So I'll just follow up through this earlier talk by Professor Goswami, the use of molecules for optical computing. And what I do in this talk, I'll try to show that the role of molecules coming from theoretical perspective, not the experimental, in nanocomputing. So this title of my talk is the First Principles Studies on Molecular Electronics / Spintronic Devices. And I'm at Michigan Technological University. Outline is coming motivation. Why do you want to study? Then I'll give you some equations because this is a theoretical talk. And then describe some of the sort of results from our group and Shashi Karna's group at Army on device elements, diode, resistor, conformational switch. And then if time permits, I'll go a little deeper and sort of showing how important nature of chemical bonding or interfacial bonding in sort of predicting the properties of these device elements. And then I'll conclude with this brief summary. So let me show you first where is Michigan Tech. Although we are in Michigan, but we are still far away. Detroit, or if you know Michigan, at Ann Arbor, which is quite far, but we are much closer to Green Bay or Minneapolis, the tip of a Lake Superior. And since we are close to Lake Superior, we have very nice sort of fall colors. This is the Michigan Tech campus building. We have a very old bridge. It used to be a copper mining area. Connecting these things, this is a canal. Michigan Tech is located next to the canal. But because of the lake, in winter, we also get a lot of snow. This is like a Cherrapunji of US. In terms of snow, we get about 200 inches per year, average. So 2 weeks ago, typically in February, we have what they call students. They create a lot of snow statues, and this is made of snow competition. But it's a nice place. I've been there for last 18 years. So you can see I have survived the weather. This is again is a group, but today I'll talk to you sort of Hein He has done most of the calculation, and so I'll sort of talk about transport in molecular devices. This is the aim of semiconductor industry: smaller, faster, cheaper. But now what we are approaching is a physical size limit. As you can see, back in 1970, we had only a few thousand transistors. For 4004 computing a CPU processor, and now as you see Itanium 2, we have billions. So what up next here? So what we are looking at is scaling standard electronic materials into molecular dimensions. This is the key thing. So let me take some example. Suppose I want to make a FET, field effect transistor, fabricate it using lattice of silicon nanowires, which again is some 5 nanometer diameter, or lattice constant, say 50 nanometer. This is a hypothetical example. So if I use it, and I use a typical doping level in the bulk silicon, which is 10 power 18 atoms of either boron or arsenic per cubic meter. So for this lattice of silicon nanowires, which is micron long, I need about 15 to 20 dopant atoms. And if I make a of crossed wires for device purposes, we are looking at approximately 0.1 dopant atom. You see, approximations are breaking down because this is sort of a limit, is a non-statistical, or perhaps sort of going to have unpredictable behavior of that particular device. Other concerns are also there. Is we have the problem the gate oxide thickness has become much smaller and smaller as we increase the CPU power. And then we have this power consumption because of the leakage current through the gate oxide. Then fabrication cost is going to be very, very expensive. And the other also thing is we use, typically industry use interconnects, copper as an interconnecting material. And as you go, this is a copper resistance, the bulk. So if I decrease the size, from say 1 micron to towards 0.1 micron, you can see resistivity is going up quite drastically. That's what you don't want to have it. And the reason of this increase in resistivity is again is because the smaller size, we have surface roughness, or surface interface scattering, and so on. So let me come to the what we call core field of molecular electronics. What is it? So what we want to basically study from theoretical perspective is fundamental chemical physics and energetics of signal transport, switching, logic, storage at the molecular level. And again, is down the road, again, if we can use application of these materials as either logic or memory units. So in this talk, I'll focus on sort of transport and switching properties. What is molecular device? So again, it's coming about few tens of square nanometers. Molecules have inherent attractiveness. What are these properties? Because of their size. Further, they represent the molecules, the ultimate in terms of atomic control over physical and chemical properties. We can precisely control the properties. And again, is control, and also we have diversity. We have lots and lots of molecules. Picking up those properties such as switching, dynamic organization, and recognition that can be achieved through such control. So these are three key things to sort of justify the use of molecules in device elements, fabricating device elements. This is a slide which we make for a funding agency, so it has lots of pretty pictures. This is a cartoon. You have a sort of a contact. The molecule again is a sketch here, but this is definitely the fabricated sort of a molecular device here. And what you can see here is a contact nickel here in this case. Tip is coming up, and this is a self-assembled monolayer of a molecule. Physics is simple. What we have, these are the contacts here. The Fermi energy or the chemical potential have a difference. So basically, and this is my molecule, which has the occupied orbitals and is unoccupied orbitals and unoccupied states. So for a higher chemical potential jumps to a molecular level and then jumps to the other end, and this is again controlled by a bias, applied bias. Now let's look at the bulk versus quantum transport, what we're dealing with. As you know, this is a MOSFET, this standard thing, and what is coming out, the current in this structure basically is a physical ensemble of electronic charge. But in molecules, if I pick up my contacts, anode and cathode, I have an acceptor and I have a donor. And they are separated by a set of insulating molecule to provide the high barrier. So what we are looking at here is current basically is a function of single electron transport. So physics is going to change. This is a theory, and I can tell you this is the first time theory has led experiment, about 20 years. Back in 1974, Aviram and Ratner had predicted a molecular device which is configuration, if you see, looks like you have again here a gold contact, and this is a pi bonded molecule, it's a different sort of kind, and similarly you can see, you can pick up another pi bonded molecule. So for this configuration, what they have predicted, electron tunneling or one-way flow of current, which we call rectification through the molecule. This tunnel current, they found it depends exponentially on the length of the molecule. If you have benzene ring 2, 3, 4, so the magnitude of the current depends on the length of the molecule. In rectifiers, which again is I showed you the configuration that it composed of donor, bridge, which is again is a high energy insulating molecule, and acceptor, and these predictions have been verified now by experiments. So what are the assumptions before I start doing calculations? So what I assume, molecule as a barrier for incoming electrons, again coming from contact A to contact B, and this again comes from the older sort of idea back in 1930. It's Landau's idea that conduction, we treat conduction as scattering in our system, and again is generalized to our metal, single molecule metal nanojunction structures. Experimental techniques to study these again is single molecule electronic transport, involve both single molecule junction synthesis and scanning tunneling microscopy or spectroscopy. So again, as I told you, in 1974, Ratner group has predicted the property of a molecule as a rectifier. Now in 97, the first time Mark Reed group at Yale have measured the single molecule conductance. This is a cartoon again. This is the picture here. Is you have a gold contacts and a molecule is sent between these two contacts. And this is gold benzene 1,4 dithiolate gold. And I'm going to refer this molecule as a BDT. BDT. This experimental result, again coming from Mark Reed's group, is this is our gold. And these you can see, these BDT molecules attached to the contacts. And when he measured the current, so the red is current on this side in microamperes, and the blue is in conductance, which is the 1 over resistance. It comes out as measured resistance is about 22 mega ohm actually. This is a wrong one. And what they also found that this IV curve or the conductance is very sensitive to contact geometry, which you expect because we're talking about nano dimensions. But indeed, this experiment has invigorated interest and activities in molecular level electronics. So let's look at the unified view. Again, coming from, again, is one of the famous theorists, Supriyo Datta at Purdue. And what he comes out is transport in these devices, it depends on your length scale. Okay. If I take my R2 is what we call is a phase relaxation length, is much greater than the channel length, then you have sort of a diffusion equation. But as you go down, when it's about equal or less than R1, then we had to use what we call non-equilibrium green function model. So I'll be sort of focusing my talk along these lines. So what are our goals? Is again using our theoretical tools, we want to identify physical and chemical mechanisms for controlled electron transport in these systems. We would like to develop and predict the properties of molecular architectures and then guide, because again this is to tell the experimentalist is what are the best or what are the worst cases. You don't have to do experiments in all the molecules, but pick few molecules which you are likely to get success, is to guide both synthesis, assembly and integration of these components. And I'll be using these so-called first principle methods based on either quantum mechanics or chemistry, the way you would like to view it, to understand these mechanisms and properties in a given molecular device architecture. This is my first slide of equations. This again is a well-standard technique because I am in a sense not a theorist but a person. So what I do is I basically take the well-established theoretical models, write the programs and apply to sort of a cases where we can predict the properties. So this coming again is 1932, I think Whittaker has done 1980 sort of modification. So what we have is the current, is the tunneling current you can call it, and I have up and down arrow. So we can have for a spin up and spin down electrons, which I'll show you later in the spintronics applications. This current, and this depends on, if you see the major functions, this is the transmission function, T, for either both up or down electrons, and this is some kind of a distribution sort of function, which you don't have to worry about it, but the key thing is the transmission function. If you look at it, what is it? It contains, is basically a trace of I have a left and right contacts. So L is left, R is right. So I have a system response function for the left contact for up and down. Then we have green function. Then we have again is the right system response function for right contact. And then I have a G dagger. So this transmission function, if you see, or rather green function, which is again is important sort of a function to calculate the transmission function, can be calculated using this equation. And what's coming out here is the important thing is how to treat this F. Because we are talking about semi-infinite contact and we have a finite molecule. That's the trick here. And all the models, approximations we use, the question comes down to it, how we treat F. So F is long-range Coulomb potential, which again arises due to equilibrium charge, both ionic and electronic, in the system, distributed in the contact region, which includes the linear voltage drop due to the applied bias at the contact point. And so again, is this theoric, the tools coming from Supriyo Datta at Purdue, Ratner at Northwestern, and Hongo at McGill. So they have different techniques of treating this Coulombic potential. So what they do is they choose this potential energy in the middle of the bimetallic junction as the energy reference for the band lineup. This is a key approximation. Then again, we have some limitations. What we assume further is we are dealing with a coherent transportation. If transport is coherent, transport of electrons, then only we can apply this Landau-Buttiker approach for our calculations. What are the challenges? How to define Fermi level? Like I said earlier, we are dealing with a semi-infinite contact with finite molecule. Bias response means we are going to apply the bias. How does it affect the molecular levels in the system? And again, still now we cannot treat the non-coherent transport, means is length dependence, or how to include the phonon effects, temperature effects in the system. So the approach is Fermi level is, what you do is basically you fix the Fermi level at the negative of the metal work function, which is well known, either from theory or experiment. And further down this is our sort of a Kohn-Sham potential, we call it, and I'll tell you a little later, is density functional theory. So what you do is you set this potential outside the scattering region to the bulk value. This is the key approximation again, and match the potential at the boundary, including the gate, to common Fermi level for the system. So what we are ensuring is the charge neutrality or sort of equilibrium configuration, equilibrium state for the transport. So let me give a few examples. This is coming from my colleague Shashi Karna's group, and what he has considered, this molecule is as a diode. So you see you have sort of a gold contacts left and right, represented by a single atom in this case. And what we do also here, because coming from Shashi's sort of experience, is greater the metal molecule coupling strength, because molecule has to attach with something. Okay, this molecule, if I pick it up, it cannot be attached to each and everything with the same sort of strength. So if you use the sulfur, if I can see the sulfur here, so basically is typically one uses in this type of calculations sulfur atom to bind with a gold atom, because gold has a very strong affinity of sulfur. And if I have very strong coupling strength, then I have the larger the current or lower the switching potential for a particular device, in this case diode. So if when we do first principles calculation, the advantage for us is we can sort of pinpoint the state of the molecular orbitals or occupied states. So this is again the same metal. We have, if I can, again, this is a bridge, this is a donor, this is a bridge, this is acceptor, bridge, and then again our gold contact metal. And if I look at the highest occupied molecular orbital, so this is similar to top of the valence band in a semiconducting material in your band gap. So what's coming out, indeed, it is located on top of the donor, which you expect. Donor is giving away one electron when you apply the bias. And my lowest unoccupied molecular orbital, which is similar to bottom of the conduction band, and in a solid, is definitely indeed is located on the acceptor. So we come to the physical intuition, and results are predicting or sort of agreeing with what we expect from this system. Now when we calculate the current, so again the start is use this first principles calculation, get the green function, from there you get the transmission function, and you plug this function to your Landau-Buttiger current, tunneling current expression. And so what it comes out, you can see is sort of this is our zero, so the positive bias, negative bias, and we have a staircase of behavior, which is for single electron current. Now you can ask the question, if you find the rectification in such a device, what is it due to? Is it due to the structural features of the molecule itself, or it's coming out of molecule-metal contact? Experiment on computer, then in the real world, as you know. So what we had done here, we have picked up this, again, is a molecule we call PM and BT. If I can read it. Yeah, PM and BT, and again it is connected through gold to via sulfur bridge. Now, if you look at the IV characteristics, so what again is coming from Shashi Karna's group. So what he has done, he said, let's calculate what happens without the molecule. So bare gold, simple here, increase the voltage, so current increases. And if I pick up a sort of a reference point as a very insulating material, there is no sort of rectification here. But if I use PM and BT, you can see a symmetric shape of this curve. So rectification is being occurred. And if you also see magnitude-wise, the current in PM and BT is much higher than so-called insulating molecule. And because of the symmetric shape, rectification is indeed being predicted here. So this is again is a diode or rectifier. Now let's come to the resistor. Experimental, suppose he comes to me and says, Ravi, I have 15 different molecules. Can you tell me which one to choose for the resistor element if I want to use it? So what we have again is a technique, is the old Marcus-Hertz theory. What it provides, it connects two-level molecular system. So what it does is basically it calculates electron transfer probability, which is a function of here VAB and density of states of a given system. So VAB becomes a measure of electron transfer probability. So what I do, I pick up sets of molecules and do this calculation. Again, you can see here dimethylene bicyclopentane. We have same dimethylene bicyclooctane, dimethylene cubane, and dimethylene dicarbodecaborane. So I do it, and then I calculate the electron transfer probability. And what I find is I have some numbers here. In these, there's a big difference. For this 222, which is octane BDT, is I have a very lowest probability related to the first, third, or fourth. So I can tell my friend. See, remember, this is without even calculating the current voltage characteristic. The simple calculation is don't consider 1, 3, 4. Just pick up number 2. And it's going to be insulating material if you want to use it as a resistor in a given circuit. Let's come to the third one, switch. Can we use the geometry of a molecule to act as a switch? So again, what we are doing here, we pick up, again it's coming from Shashi's group, with Ranjit Pati, who now is in our department, is you pick up this so-called coplanar conformation. You calculate the current, and what you find is, aha, you have some IV characteristics. Now what you do, if you see this molecule is in plane, start rotating the molecule. And what's happening here, you discover when we have a perpendicular, this molecule is perpendicular to this plane, you do not have any current flowing through the system. So you call it off state. So you can see again here is we can use this intrinsic molecular mechanism for switching electrical characteristics. Let me switch gear a little bit. So far what we had done with electronic charge. See if you can use the spin property and find the applications of these molecules in spin-based electronics. This, you know, this is standard quantum mechanical stuff, but what it comes out in ordinary electric circuit, the spins are oriented at random. Therefore, they don't have any effect on current flow. But in these spintronic devices, we have to have a spin polarized currents. Then only we can use this properties of a spin to control the current flow. So let me again define some variables which I'll be using it, is what we call is a JMR. is junction magnetoresistance. So what's happening here, if I take my magnetic field is 0, I have two magnetic contacts. It's not gold in this case, but has to be nickel, cobalt, iron, because it has to be magnetic materials. See, their spins are aligned opposite to each other, called anti-parallel alignment. So our non-magnetic molecule, there is no current flow here. But if I apply the field and flip the spin of the second contact, you can see the charge electron is sort of being passed through this device, the system. So what's happening here, what we call a spin wall effect, that the conduction electrons which are going to flow experience a different resistance when the spins of these contact electrodes are aligned in parallel or anti-parallel. So I define my JMR as this ratio where resistance anti-parallel, negative resistance parallel over resistance of parallel. Now let's do some calculations. So typically these sort of, as you know, is people use is STM setup to do experiments. So I pick up again similar setup. So what I have here is a magnetic substrate, in this case nickel 11, and I have a self-assembled monolayer of either this BDT, which is benzene 1,4-dithiolate molecule, or BCO, which is bicyclooctane. And if you remember from the last work, we found that BCO is to be an insulating molecule. And the reason being here is it's called sigma bonded molecule. The charge density is very localized. On the other hand, BDT is sort of pi bonded molecule, so it's delocalized charge density. So this is my substrate. This is self-assembled monolayer of these either BDT or BCO, and this I use a tip. A tip has to be magnetic because you're talking about spintronic applications. So what I do is, again in simulation, is I simulate this semi-infinite tip. The tip comes out like this, so I can pick up the cap of the tip, either a single nickel atom or sort of clusters of 5 nickel atom or clusters of 30 nickel atom. In this way, I also can study the size dependence of this cap of the tip on the current. The second slide of equations. So since we are using this STM setup, so we have a little different equation. So in this case, the current, either spin up or spin down, it's coming out, if you see, is a convolution of density of states of the substrate and density of states at the tip. And then you have this channel going from some energy values, which we call negative E over 2 over E over 2, and these are sort of a distribution function, and you see the exponential factor is sitting up here. Again, physics is the same, is you have the tip, has a higher Fermi energy or occupied states, so electron is flowing basically from tip to the sample. So how do we do the current calculations? As I told you earlier, current is basically a function of the convolution of projected density of states of the monolayer at the cap of the tip position and density of states of the tip. Now, we use these first principles methods to calculate density of states. It can be either Hartree-Fock or DFT level of theory. So what you do, you perform these calculations and then extract a Fock if you use Hartree-Fock, or Consham if you use DFT, eigenvectors in the k points defined by the standard technique, what we call Pack-Monkhorst net. So this is well known. And again, we take care of the semi-infinite nature of the tip by broadening of the density of states. So this is another approximation actually one should be aware of. Let me show you some results. So in this case, I have a nickel substrate, I have a BDT, which is pi bonded molecule, and I have a tip of nickel. Now, this parallel spin up, it means my tip and my substrate spins are parallel. And anti-parallel means they are anti-parallel alignment. So what I'm looking at, if I take my tip to be 13 atom nickel cluster, this is red is shown by the parallel alignment. And if I look at the anti-parallel case for the again nickel 13 cluster as a tip, the current is given by green. So you do see there is an effect of a spin flip. And that's what we call is JMR when we calculate it. Similarly, we have found for both nickel 5 cases parallel, anti-parallel, a single nickel atom parallel and anti-parallel. So there is an effect. Now you can ask again is why? What's happening in the system? Current is flowing near the Fermi energy. So I had to have a occupied states, number of electrons available at the Fermi surface and near the Fermi surface. And these electrons are going to the unoccupied states. So I had to have those number of states available. Then only electron can flow. So you can see when I have the parallel spin alignment of the substrate and the tip, if you look at the spin up, there is nothing here. There is nothing here. But for spin down, there is a large number of electrons are available to jump to these large number of unoccupied states. Okay? Let's see what happens when we spins are anti-parallel aligned anti-parallelly, substrate and tip. So in this case, I'm going to go from up, which we don't have anything, to down, which we have anything. But electrons will not flow because nothing is available here. For spin down, we do have electrons, but they are not, number of states are available. So you can see again is simple physics. You don't have to do fancy calculations, just calculate the density of states and see if you have those available states near the Fermi surface in the both occupied and unoccupied region. So this gives you qualitative trend. But if you want to know the quantitatively, then you do have to do those calculations. Now let's ask a couple of questions, because again, being physicist, not an engineer, we have to ask questions. Paul is nodding. So first question is, what is the role of molecules? If I have a BDT, which is a pi bonded material, as molecule, I replace with BCO, which is insulating sigma bonded. What happens to the current? Then also is we have to again investigate the nature of magnetic electrodes. I have shown you example of nickel-nickel. What happens if you have nickel-cobalt or iron-cobalt? Again, the binding with the substrate, because for these ones we use sulfur. Can we use some other atoms? And finally, is what is the influence of the monolayer coverage on the substrate, on the magnitude of the current? So let me pick up only first two, so which I will talk to you about nickel BCO nickel. So earlier I had nickel BDT nickel. Now I replace with this sigma bonded molecule, and again similar setup, STM setup. We have substrate, self-assembled monolayer, and we have tip separated by a small vacuum. See the current. So again, PL is parallel, AP is anti-parallel. So if you see the red is for BDT, and if I look at the PL for BCO is green. Anti-parallel is blue, and again is anti-parallel for BCO is in this color. So there is indeed a difference between BCO and BDT. Again is why. So let's look at the density of states, which comes from first principles calculation. And you do find, indeed, there is a magnitude-wise, this is a BCO, this is BDT occupied states near Fermi energy, and this is unoccupied states here you have. So even the small difference in the magnitude of density of states is giving you a larger difference in the flow of electrons in these two systems. We can go further down and see spin density. Means what is the polarization? This is again is the theoretical results. So what you see here, the BCO, which is again a sigma bonded molecule, is very insulating. You have a lesser degree of polarization compared to BDT, which is pi bonded molecule, has a very strong polarization. So again, this gives you sort of a predictive power of a calculation. Total experimentalist, if I have a strong polarization, this is a substrate and this is a tip here, up here, in a molecule is likely to have a better candidate for your device applications. So let me summarize this part. is we have studied the nature of subchemical bonding versus spin-dependent tunneling current. And what did we find is indeed the BCO, which is a sigma bonded molecule, has smaller and more localized spin polarization, which mimics its intrinsic chemical bonding features. So lastly, let me show you the requirement of bonding with the substrate, how important it is, the interface bonding features. So for this case, I again switch gear from an organic to inorganic case, and I pick up nickel C60 nickel. As you know, C60, this is again the charge density distribution. So you can see our semi-infinite nickel substrate is fairly well bonded with the C60 cage. Now C60 cage, on the surface, it has 5 member rings and 6 member rings, or combination. So we have a lot of various binding sites for this contact nickel atom. So let me call is these sites, pick a few here, B for bridge site. So I have B66 means this nickel atom, this is a contact nickel atom, attached to our C60 cage on the bridge when we had 2 6-member rings in the vicinity. On the case B56, we have 6 and 5-member rings. Similarly, I can say H6 is a so I have a sort of this contact atom is sitting in the sort of a hexagon, but for H5 we have pentagon. And you can have similarly sort of top side on the 5-member ring, or T6 top side on the 6-member ring. But for this talk, I'll just pick up these 2 representative cases and show you some results. So if I take my contact to attach to either B66 side, so I have again is in parallel alignment, both left and right nickel contacts, current is coming out in blue. But if I look at the whole, red is the B66 side and blue is H6 side. There is a big difference here. So indeed, interfacial bonding features are very important in predicting the IV characteristic of a given molecular device. Let's look at the JMR effect. Is B66 is in red. Again, if the applied bias remains sort of flat, about 100%. But for S6 side, there's a large variation with the applied bias. We found an experiment, again it's coming, I think it's from Dan Ralph's group at Harvard, I think he's at Harvard, and what they have studied sort of Kondo effect in the presence of ferromagnetism in nickel C60 nickel system, and in one of the graphs they indeed have found this JMR value is close to about 80%. And if you remember, our values are coming out 100 and 150%. So it's a fairly good result, and which gives you confidence in our modeling tools. Now you ask the question why? Why B66 has a lower current or sort of a, lower current over S6 side? So here I plotted the transmission function. For these cases, so my Fermi energy is aligned at 0. So this is a parallel spin configuration of the contact atoms, and this is anti-parallel. So what we see here, this is a band gap. It represents the band gap of C60, which is insulating molecule or a sort of a material. But we do have some sort of a broadening in B6 case or some peaks. Okay. So what's coming out is we had to have a mid-gap state so that we can use this nickel C60 nickel system for spintronic device architecture. Okay. So this is one prediction. You have to have mid-gap states. Now you can ask the question is what are the nature of mid-gap states? Why do we have to have it? What happens? So what we do, here we can use also the multiple levels. We can plot it. And we can project their nature towards the constituent atoms. So what we find here is these, for the spin-up state, indeed we have a mid-gap states coming out in our molecular levels, which are related to this broadening of the curve for B66 side. Similarly, for H6 side, which is a higher current, you can see again this mid-gap state is showing up here, related to either peak in transmission or density of states. For the antiparallel case, we don't have any peaks. Okay. So again, what you can do further, you can again, like I told you earlier, is project out it on your atoms. And we find for C60, this is our lowest unoccupied molecular orbital, is all localized on C60 atoms, carbon atoms in C60 cage. But for the HOMO cases, you see that the hybridization is showing up between the contact atom and the carbon atom of the C60 cage. So again, what's coming out is one has to have mid-gap states to get the higher JMR effect, and the nature is the hybridization between a contact atom and the carbon atom. So you have to choose the contact atom such that it hybridizes with carbon molecular levels. Let me again summarize, is indeed we have found that current shows a significant site dependence by the bridge or whole site. We have to have these gap states both in parallel spin configuration, which means a higher transmission near Fermi level. And then again is higher current we have found is about 100% JMR for B66 site and for 200% about for S6 site, and experimentally is about 80%. So this ends what we have done so far. Is now we want to go further, see if we can develop the techniques or theory tools so that we can treat the external fields self-consistently in our calculations, and we further sort of choose, with again help from experimentalists, a different architecture for either diode or a transistor using these molecules. And this is again is a cartoon. You can see here is we have a substrate, we have a gold nano interconnects here, and these are the carbon nanotubes proposed for heat sink. And Dr. Yap on Wednesday will talk more about these carbon nanotubes. And this small scale basically is nothing but our 3-terminal decide, 3-terminal device with the source, drain, and gate. This is again is development of theory, because is how real we are in our predicting the properties. And we can see we have not taken care of the time dependent behavior, which is very, very important. And there are ways to do it. Is first thing is what happens with the time. What is the time dependence of conformational changes and how do they affect electronic behavior? Then you have effect of contacts, dynamic characterization of metal or semiconductor contacts. And then finally we have electronic quantum effects, means what is the frequency dependence of these transmission functions as a function of structure, length, and temperature. So indeed, a rich variety of molecules and electrodes needs to be explored. And in terms of the device elements, we can again propose these molecules as both passive or active elements, as eternal junctions or rectifiers, or switch junctions, or single molecule transistors. But let's look at the experimental point of view, because there are a lot of problems in fabricating these predictive sort of architectures. The question is how you control this molecular contact at the interface, which you have seen is quite sensitive. Then we have to worry about the environmental influence. And then how, again, is to generate these complex patterns, because they're going to increase the density, and how to pack a molecular system in such a small chip. But there is hope, because again, this result came out from Mark Reed's group, experimentalist, in 2005. And indeed, they have sort of fabricated a molecular device, which we call planar fabrication. So you have these contacts, and this is self-assembled monolayer. It's coming out here, it's represented here. And you can see the IV characteristics is fairly smooth. And indeed, it is temperature sort of, if you see from 90K to 250K, it's fairly stable. Let me thank the funding from my DARPA Army Research Office, my colleague Shashikana from Army Research Lab, and a colleague again is Ranjit Pati, and the grad student Haing Hay, who has done most of the work with the Kachan and Gautam. Thank you.